First, I would like to introduce myself. My name is Jürgen Wild. I'm professor here since 1999. Before that time, when I studied material science. Later on, I worked and did my PhD in the field of bonding wires, and that's why I stuck with assembly and packaging technology. In assembly and packaging, reliability is a very important issue, especially under the aspect of physics of failure. In this lecture, I would like to extend the view going more to the system level of reliability. So what I would like to give you is a comprehensive view of important aspects of reliability engineering. So there can be lectures which are more in-depth, but what I would like to give you is an overview of the most relevant tools we have here. Okay, let's go ahead. The next 2 pages are related to the question, what is reliability? Can you give me your idea what you think reliability is? What is meant by reliability? I hope you can unmute yourself in that system. Okay, now let's try. Can you unmute yourself now? Okay, fine. So, what do you think reliability engineering is? Or what is reliability? No idea? Or
I have a really maybe not precise idea. It's a kind of measure of quality of something that we are interested in.
Yes, unfortunately, I still have another problem. I cannot get this thing here writing. So it is an aspect of quality that is correct. So we can say reliability is a probability, and a probability is something that goes from 0% to 100%. So when something is highly reliable, we have a probability that it works or that it is alive as a system of 100%. And over time, the reliability goes down. On the other hand, we must say reliability is not, it's not so easy to understand for individual components, but it is more to be understood for a set of components. Imagine we have 100 components and let them work, and after some time maybe 10 have failed, and then 20 and 30 and so on. And so we can say the reliability is 90%, 80%, 70%. So it's a probability of survival or the probability that it is functional after a certain time. Okay, so reliability. That's, you could say, the probability of survival and it goes from 100% to 0%. I don't know why it is not writing here. So it's a probability of survival, 100% to 0%, and it only holds for non-repairable systems. So normal technical systems are repairable. For instance, we have a car or an aircraft or a whole system like the tramway system in Freiburg. All of these are repairable, but non-repairable is, for instance, a single electronic device or a single component. In most cases nowadays, it will not be repaired, and in that way reliability is limited to these. Okay. Reliability also is an aspect of quality. We can say that. You could say quality refers to 0 hours. So that means how good is a product? Is it fit for use when you just produce it? And reliability in some way means quality over time. Okay, here it limits, and that means the aspect of time is very important in reliability. So there are typically definitions in standards which have been published, and important standards are the IEC, that's for electrotechnical applications, and ISO is, let's say, for other. Rest of the world, mechanical engineering, car industry, and so on. So IEC means International Electrotechnical Commission, while on the other hand, ISO means International Standards Organization. And the IEC and the ISO are the most top-level standard organizations worldwide. So you could say in some way standards are the more important, the higher their global level is. Standards are not law. Standards are some descriptions or regulations which can be made part of law, for instance. And So law can require that some reliability is according to some standard, for instance, but the standards organizations are independent transnational organizations. And both have defined several termini, and the top level terminus in that field is dependability. So in normal language, in English, you can say he is a reliable guy or she is a dependable girl, and that means very much the same. In reliability engineering, the whole set is defined by dependability, and it summarizes reliability, availability, and also performance over time. Performance over time means, for instance, you have a car and it got, let's say, 150 kilowatt of power, but when it's older, the power decreases, and due to degradation of some parts of the machinery, and so it only has 130 kilowatt of power, and that would mean performance is degraded over time. In this lecture, we will treat reliability and availability and also the behavior over time, but not performance over time. So, as I mentioned, reliability defines the survival probability after operating time t. That is important. So I have to go back here. Imagine I don't know what's going on here. So let's try it here. We have reliability, and here we have time. And so the maximum of reliability is 1 or 100%. And in some way, it goes down over time. And here I made several curves. And why would there be several curves of reliability over time? Let's say time can be in hours or in 1,000 hours or so. Why could there be a different behavior of reliability over time? So that means you start with 100 and then you get less and less. After some time, you only get 0.5, for instance, or some other time you only have 0.1 or 10%, 50%. Can you give me an idea why reliability would go down differently? Yes. Can you give me feedback?
Yeah. Maybe because of different quality levels of certain.
Yeah, that is correct. The quality level can be different. So here we can say reason. I abbreviated quality level. Yeah. Now imagine cars, yes? Imagine a car driving in Central Europe, like in Freiburg, and driving around here, let's say under normal conditions, and the driver is having a moderate driving style. And on the other hand, you have someone in, let's say, in some backyard of Asia in the desert, and driver is driving like hell. Yeah? What is different here in these two conditions? So it's the environmental and the loading condition. So it can be the load. So if you drive faster, if the road is worse, or you don't even have a road but only a track, then you could say there is a much higher load on the suspension of the car, a higher load on the engine, and so on. And of course, a device that is loaded in a more harsh way, it will degrade earlier. Okay, so now we have learned reliability is the probability of survival over time, and it will always decrease. Reliability could increase again, but in that case we would have so-called repair, and then it would no longer be a non-repairable system, of course, and so by definition reliability will always go down. So then we have the question of safety, and safety is something also which is important, that is not just the question if it failed or not, but safety is a status when the risk of damage is limited to an acceptable value. So it is the risk of damage to persons or property. In this case, the risk will not exceed a maximum acceptable risk. Okay, now the question is, what is risk? On the risk is something, I would say, on the bad side. What is on the good side is you have a good chance, yeah, of winning, for instance. And a risk is defined by the probability of some event happening. Here the probability is used with an H. Unfortunately, we have for risk also an R, like for reliability, but that's not the reliability R, but it is the probability of an event which leads to a damage, and S is the amount of damage which is caused by the event. So you could say if you have a medium probability of something to happen, and what follows from the event is maybe also medium severe, then you have a certain risk. On the other hand, you could have the same numerical risk if the probability is very, very low, but if the probability is very, very low, but the severity is very high. On the other hand, you could also say, okay, it is very probable, but not much will happen, severity is very low, and all three events could have the same risk. On the other hand, when you plot risk, you have here the maximum acceptable risk. That's a limit, and here you are safe, and here you are in danger. That means whether something is safe or whether something endangers you is a question of how the maximum acceptable risk is defined. When I was young, nuclear energy was introduced in Germany, and there was a very fierce discussion about whether nuclear power stations are safe. And now the question is, are nuclear power stations safe or not? What is your idea? Are they safe or not? Yeah, please go ahead. Or is there a more, let's say, intelligent statement about safety or non-safety of nuclear power stations? We must say it again depends on the maximum acceptable risk. But on the other hand, you cannot just define the maximum acceptable risk in an arbitrary way. Yeah? You cannot just say that's a number and that you have to deal with, but such maximum acceptable risk must be defined and found in a proper way. And there are several aspects. For instance, one is ethics, yes, so that you avoid damage to people or death of people. On the other hand, you could say, what would be a maximum acceptable risk for a new technology? Then you could say, if I have a similar technology, for instance, you have a new vehicle type, and that new vehicle has autonomous driving. Yeah? And now you would say, when you go for autonomous driving and the maximum acceptable risk is not higher than the typical risk is in normal piloted driving, then you could say, okay, that's possibly an acceptable value. Yeah? On the other hand, you also will have a chance that you decrease that maximum acceptable risk because your autonomous driving technology will become better, and in that way you can find a maximum acceptable risk. Okay, but there was very much misunderstanding because that concept of maximum acceptable risk was not properly understood. Okay. Danger. So when the risk is higher than the maximum acceptable risk, we are in danger. So then we have other words which are important. We have a fault, a defect, and a non-conformity. All three are non-fulfillment of at least one of the requirements to a unit. Typically, a fault is used for logic states. For instance, you have some faulty bit in your computer. The calculation fails, therefore, but when you reset your computer or when you restart your program, all is fine. You have no permanent damage. In case you have a permanent damage, in most cases to hardware or to material goods, it's a defect. And the failure is the transition from a non-defective to a defective state. When you go from a defective to a non-defective state, it is a so-called repair. Okay. So non-conformity is general non-fulfillment of requirements. Defect is mostly used for hardware, and defect is mostly non-repairable, and it is permanent, while on the other hand, fault is more a logic state or a state of operation that is not okay, but which can be reset, for instance, by software operations or by switching operations or something like that. Okay, so we had some definitions, and now let's again repeat with the diagram of unfortunately, that system doesn't work as I would like to have it. Let's say here we have, now we make 100%, we can also make 1, and reliability goes down over time. On the other hand, so that is R. On the other hand, we have the probability of failure. And that probability of failure is the so-called failure function. Both are complementary values, and you could say if is 1 minus R. So the failure probability is 1 minus the reliability probability, and that is a very important and basic function. That is now a question. When I give you a reliability value, let's say, for instance, I give you a reliability value of 99%. What other data do I have to give you? Okay, go ahead, please. What is, so a reliability alone will not be sufficient information. What is the second which we need? Can you give me feedback? So please give me feedback. What information do we need? Of course, the second information always is time. So we give a combination of F and T, or a combination of R and T. And that means, for instance, the survival probability after 1,000 hours, or what we could also give is the mean time to failure. What is mean time to failure? Mean time to failure means when I take the survival times of all different samples and take the average of these lifetimes. Yeah? So here, maybe the first died, the second, the third, fourth, fifth, sixth, and here the last. Then the average lifetime is the mean time to failure. Do you have an idea what is the proper probability which is connected to the mean time to failure? What is the probability of failure when we have reached the mean time to failure? Okay. Do you have an idea? What is the probability of the mean time to failure? That is depending on the distribution function. And the distribution function can be, for instance, Gauss distribution. In that case, the probability of failure would be 50%. But in many cases, it is just 63% when so-called Weibull distribution holds. Okay, let's go ahead. So we have lifetime parameters. We could say we have times when 5% failed, T10, 10% or 50% fails. And the mean time to failure is, yes, it's the average of all lifetimes we have in a system. And in the case of a normal distribution, the MTTF is just T50. Again, MTTF is used for non-repairable systems. When we look at, for instance, MEMS or other electronic devices, it should be the proper term we use here. In case we have a repairable system, we use the so-called MTBF. It is the mean time between failures of repairable systems. But we will see that later on. Okay, now another aspect which we already were touching is the availability. So you could say, what is availability? It's an important factor. For instance, when you buy a more complex system. Imagine you buy a truck, or you would buy an aircraft, or you would buy a tramway, for instance. Reliability could be one aspect, but on the other hand, you are not just interested in the question, when will the first failure be, but what you are more interested in when you operate such a system over, let's say, 10 years, how many hours could you use that system? And so normally when we have such a system, we could say we have the time and we have we have operation, we have repair, we have operation, we have repair, we have operation, repair, and then, so let's say operation, repair, and also after some time maybe we have so-called maintenance. So maintenance means we have a system that is still functional, but we overhaul it. For instance, it goes into a workshop for some time, and many wear-out pieces are replaced. For instance, the brakes, the fluids are exchanged, and so on. That is maintenance. So maintenance means we work over a system that is still functional, and repair means we do it when the system has failed, when it is in a defective state. Okay, so we have the mean time between failures, so that could be operation 1, operation 2, operation 3, op 4, and so on. That gives you the mean time between failures. Then we have the mean time to repair. Repair 1, repair 2, repair 3. Of course, the times of repair can be different. So we have a mean time to repair, and we have a mean time to maintenance. Times where the system is not used at all, so where it is just stored away, are not counted here. So it is only the time where it could operate. And so again, that's a time between failures, that's a time to repair, and the time it takes for maintenance. And so the average probability is the mean time between failures, then when it works, divided by the mean time between failures, plus the mean time to repair, plus the mean time to maintenance. So in that way, we can compute availabilities. And nowadays, when some operators of complex systems, especially in traffic systems, operate these, they make a contract with the supplier, and the supplier has to guarantee a certain availability. Of course, that's not so easy, because the availability again depends on the quality of maintenance and repair which the user has. Okay, but in the end, the user wants to have availability which is as high as possible. Okay, now how can we define reliability? We have already seen it, and it should be always taken on a statistical basis. And reliability, as I said, it makes no sense to use it for a single device. It always makes sense for a certain set of devices. And that set is defined by the number of devices which come into Sorry, I have to get my stick back. So, n is the number of devices which come into life or which are produced or which are part of the set is tested. After some time, n have failed, and so the reliability is 1 minus n divided by n. The failure function or the failure probability is just 1 minus r of t. Or you could also say f of t is n divided by n. So just easy, 1 out of 100 has failed, so we have a failure probability of 1%. As I mentioned, we have the so-called mean time to repair. And the mean time to repair is again defined on the basis of the failure function, and we could say the mean time to repair is when, so that's r of t and that's t, when you take the area under the curve. So reliability over time. And you divide it by the width here of that curve, then you just get the average reliability, the time for the average reliability, and that's mean time to repair. So in fact, if you write it precisely, then it's just r of t dt integrated from 0 to infinity, so that's the area here under the curve, divided by the width, and as reliability can only go from 0 to 1, that is this delta r, and that is just 1. So in that way, we have a very clear definition of mean time to failure, and in that way we also see that mean time to failure mainly depends on how this curve goes here. Now, in that case, it's important to look at distribution functions. Here I made just an arbitrary sketch of reliability goes down. That would be, let's say, a typical assumption for a relatively long time. Reliability only decreases slightly, and then it decreases more in a stronger way, and in the end, for the last ones, it takes very much time to fail. So that would be a typical behavior of such a curve, and now we can look how such curves will look like. Of course, when we just take a normal distribution or a Gauss distribution, we take here and we take f of t. That's the so-called density function. The probability in the Gauss distribution is going in that way, and here again we would have the mean time to failure, for instance. Okay, so we can also say we have the density function and we have the cumulative distribution function, but that's a basic thing in statistics. So typically we can say the distribution density function is the first derivative of the failure function derived by time. The failure function itself comes when you have the density function and you integrate it from 0 to t, then you get the failure function f of t. And here there are several functions which can be used, and the most simple function is the so-called exponential function. Again, we take the integral form or the cumulative form. F of t is 1 minus e to the power of minus lambda t. Lambda here is a constant parameter that is the so-called failure rate. On the other hand, when we take the inverse of lambda, we get something like mean time to failure value. Another function which is very similar to the exponential function is the function made by Mr. Weibull. It looks very similar. It's 1 minus e to the power t divided by tau, which is a characteristic lifetime. In normal processes, you could also say that's a time constant to the power of beta. As we see, when the beta is 1, then we just have the exponential function as a special case of the Weibull function. Another function which is sometimes used is the log normal distribution. So we do not take distribution over time, but we take distribution over logarithm of time. That is just for completeness here. We do not need log normal distribution in this lecture anymore. In some cases, it's mathematically easier than to use Weibull function, but we don't need it, so we will not treat it. Okay, so we have seen in such distribution functions, we have the cumulative distribution, and the result can always be from 0 to 1 or 0% to 100%. Okay. Here that is a percentage per time interval. So in that case, it means it's the density function. And there is another term which is the so-called failure rate. The failure rate is defined as the rate of failing parts per time related to the parts that exist at that time. So imagine you know there is a certain number of cars in the field, and you know how many cars there are, and you can count them, and you also can count how many cars break down per week, for instance. Okay, then you could say you relate that breakdown to the numbers of cars which exist. What you don't know at that point of time, if you do not have some historic information, is how many cars there really have been. So that means you could determine a failure rate. That means how many cars break down per time in relation to the cars existing at that time. But you do not have a density function as long as you do not know how many cars in total existed at the beginning. So failure rate is sometimes more convenient, but the mathematical definition of failure rate is it's a density function divided by r of t, And as we see, R of t goes down over time, but up to short times, R of t is almost 1. And so you could say at short times, the failure rate and the density function are typically very similar. Okay, so we have seen quite a number of mathematical definitions. We have the distribution density, we have the failure function, we have the failure rate, and we have the mean time to failure. And I must say, when you come into my exam, it is of absolute importance that you know these definitions and you know how to work with these. Also, I would like to mention that for the future, for the understanding of very many aspects of this lecture, the knowledge of these 4 definitions is very important. And so how these are interdependent, and on the other hand, it is also of utmost importance you know how exponential function and Weibull function are defined as a cumulative distribution. All other aspects like density function or failure rate or mean time to failure can be derived easily when you know these 2 definitions here. Okay, so now let's have a look at these distribution functions, just how they look like. That here is the beta. In some of my publications, I still use the b value, and we can see the failure function depending for a Weibull distribution, depending on that beta value here. So if the beta is 1, so it just goes up in a monotonic way, and we do not have a inflection point. Also, below 1 for the beta, for instance 0.5, we have no inflection point in that curve. It just goes up, but the slope decreases with time. Here we see that is just 1 lifetime. You could say it is roughly 1 MTTF. Not precisely, but roughly. And so above 1, when we have a small beta, we can say the distribution function, the failure function, goes up very fast. So the very first failures come very soon, but after a limited time, the increase of failures is only very slight. When we have a beta value above 1, we already get here an inflection point, so ein Wendepunkt in the curve. And so we can see, for instance, for a value of beta is 5, for a certain time, almost nothing happens. So, in fact, the failure, the total sum of failures is almost 0 for quite a long time, and then it goes up very rapidly, and also after a certain time, virtually all samples have failed here. So that's a design we would like to have. Why is it so? In that way, we can predetermine the interval in which our products will fail very well. Please note that these curves are only valid when all specimens have the same load. And in real life, of course, that is not the case because every car is driven in a different way. But here we can say only when this beta value is high or even higher than 5, the designer can predetermine the lifetime of the product. In other cases, there is a large scatter, and in that case, you cannot do much about it. If the scatter is there, the lifetime distribution is wide. Here, the reliability is very simple, so I do not have to discuss it. R is 1 minus F, so it's just the complementary function. When we take the density function, so we can see, for instance, for certain beta value, we have in the density function a bell shape. Again, please note that is Weibull function, not Gauss distribution. But in cases where the beta in a Weibull function is between 2 and 5, you could typically say it is very hard to distinguish, is it a Weibull, is it a Gauss? But in reliability engineering, it is convenient to use Weibull distribution. In mechanical engineering, for instance, where just the strength is distributed, we can say the mechanical engineers typically use Gauss distribution, while the people more oriented in a chemical way, for instance, in ceramics industry, they prefer Weibull distribution. Okay, so in fact, for beta values from 2 to 5, it is quite hard to distinguish, but in reliability engineering, we use typically Weibull distribution. When we divide, so here we have f of t, and when we use the failure rate, h of t, and we divide it by r of t. So r of t is just the surviving portion. Then we do not have a maximum anymore, but the curves look relatively, we have a decreasing failure rate for small beta values. We have a constant failure rate for beta is 1. And we have an increasing failure rate for beta values larger than 1. Okay. In that way, we can see that it is very important which distribution function we have to assume in our system. Again, what we are seeing today will be an important tool for the understanding of more complex behavior. Okay, give me a second. I would like to start Okay, let's go to the next part. My question is, can you still see my screen? Number 2, dependability of mechanical systems.
Yes.
Okay, thank you for the feedback. Yeah. Why do we start with mechanical systems? That is something which is very important because in the 18th and 19th century, also the safety of many systems was depending just on one single component. So that meant if you have a crucial component in your system, if that system fails, your complete system will fail and you could have a very high severity. And just to give you some examples where single components failed. For instance, here on top we have, we have here typical fatigue failures. For instance, in that lower left case, a turbine blew up in an aircraft. That can be very dangerous because when the turbine blades fly away, when they break, they can fly through crucial parts of the aircraft. For instance, they might sever the control which gives control over aileron and so on. And in that way, just by a crash of such an engine, the complete aircraft could be lost. Here we see a typical example of such a fatigue failure. Here a crack started and it developed in the part until at some time the crack was so large that the part was weakened very much. And when this part was weakened too strongly, it just broke. So that's a typical event. We have a fatigue failure which grows gradually. So we have a small crack, maybe only growing with a rate of, let's say, 10 to 100 nanometers per load cycle. But if there are millions of load cycles, it will sum up to millimeters or centimeters, and finally the part is breaking. Here it is a windmill. That is a very severe accident which happened almost 25 years ago in Germany. Here in a car crash, in a train crash, we had 100 dead people. Fatigue is a result of cyclic loading. So in fact, you could say it's a result of some kind of vibrating load. And it's responsible for more than 90% of all mechanical failures. And if you look after fatigue in Google Scholar, for instance, you find 4 million results, publications on that topic. And so it's of utmost safety and economic issue. And it is important, of course, to know about the influences of fatigue and fatigue lifetime. And of course, it makes no sense to think about safety of systems when you are not able to deal with the reliability of the individual components which make up your system. So that's a reason we do this bottom up, and also it is something which is viewed in a historic way. So that's an image I took from the internet. You can see here a bridge. The train raced into that bridge, and the bridge was destroyed. The garden of that house was destroyed, and at least 5 of the cars of that train were completely lost, including the people who were in that train. So it happened in 1998. The train had a speed of 200 kilometers per hour. It's not so much when you think about the speed of modern high-speed trains, but what happened? It was a broken wheel. That broken wheel was a fatigue failure. And what happened is, we have the wheel, and the wheel has a ring. That ring is made of a special steel, and in between the ring and the very wheel, there is a rubber. The rubber is only for comfort reasons, so it is damping the vibration, because at a high speed you have a vibration which is transferred from the rail to the wheel, and if there is rubber in between, like in your bicycle tire, then it is just damping. Unfortunately, these rings here, they get ripples, and in order to remove these ripples, they must be turned down. And the reason what happened and what led to the crash was the following. Here we had cracks which developed due to fatigue, and that weakened that ring. And on the other hand, by turning down the wheel over time, the ring became thinner and thinner, and at some point of time the ring was too thin and the fatigue crack was too long, and so this ring just broke. Unfortunately, it just broke directly before the train met the bridge. The train was derailed, and the derailed wagons were running into the pillars of the bridge. The bridge collapsed, and it buried the rest of the train, and that was the reason for these many fatalities. As an engineer of material science, I'm extremely sad that this happened, because that was a typical accident which happened before in the 19th century. It was very frequent, let's say up to 1880 or so, and then in Germany very much research was performed in order to clear up this phenomenon of fatigue. And and fatigue is mainly a result of the loading conditions. So if we have a mechanical part, we can load it in a different way. Imagine we have a string, and you hanging from the ceiling, and you put a weight to that string. So you could say, depending on the weight, you have just a constant load. So some materials just tolerate it, so you can hang something to that string until infinity or almost infinity. It just will tolerate it if the load is small enough. What we put here is the stress, and the stress is force divided by area. So you have a cross-sectional area of your string, let's say 1 square millimeter, and you hang 100 Newton to it, so your stress is 100 Newton per square millimeter. On the other hand, often you have just a monotonous loading. That you often do in materials testing. You just pull it until you pull it apart. So that's a monotonous tensile test or a monotonous compressive test. And here we have a maximum load, a maximum stress. And of course, always in these cases here, the initial slope defines the Young's modulus. Okay, that just gives you an information. What would be the maximum strength of your part? And when you are a designer of your course, you will never be allowed to make a design where the load is higher than the strength. Typically, you have a safety factor, like a factor of 2. So if you have just, it's just monotonous load, and so you would say the strength of your steel is 1000 Newton per square millimeter, then you would make a design with a safety factor of 2, and so you must be sure the maximum load is never above 500 Newton per square millimeter or megapascal. Okay. On the other hand, it was found out that such a safety factor is often not sufficient when we have an alternating load. Imagine we have a loudspeaker, and that membrane of the loudspeaker is hanging on some suspensions, and so you just by movement of the loudspeaker we have a certain back and forth movement, and that will lead to an alternating stress. For instance, that stress can be constant and have a constant frequency. So that would be a sound to your sound speaker which is only one tone. On the other hand, what is in all technical applications more important is we have a variation of the amplitude. Also, we could have still a mean value of stress. For instance, in our wheel of the train, we have a mean value of stress because the train has a certain weight. And on the other hand, by the revolution of the wheel, we get an increase or a decrease of the stress in the material. But on the other hand, stress over time can be just very arbitrary. What I would like to point out is that it is well established that in fatigue, the frequency of the testing or the frequency of the load is not of importance. So when you have a fatigue problem, it doesn't matter if it is at 10 hertz or at 1000 hertz. What counts is the number of revolutions or the numbers of mechanical cycles you have here. Of course, if you have a low frequency, it takes much longer until you reach 10 millions of cycles, for instance. Okay, that's fatigue, and fatigue is a result of alternating stresses in a material. So the question, that could be also a question in an exam, will the loading type have an influence on lifetime and reliability? There are constant loads or constant stresses, monotonic stresses, cyclic stresses, or variable stresses. Question also is, what is the load on a component? Is it always the stress we have, like it is used in engineering, or what else could it mean? And also, generally, what is fatigue? And for instance, what is the SN curve? For the Americans, it's Baskin's SN curve of fatigue. Okay. There is a second effect which is also a risk factor. So we have seen alternating loads will lead to the fact that a stress that is tolerated is significantly lower than the stress just in a monotonic test. On the other hand, people made the following experiment. You have a shaft, and that shaft is pulled. When the shaft has a uniform thickness, it has a constant stress over the cross-section. Now imagine you hide that shaft in a shaft which is thicker, but which has a notch. And it was found out that when you look at the residual cross-section in between the notches, the stress is different. At the tip of the notch, you will have an increase of stress. That is very important, and also that was one factor which led to the improvement of mechanical shafts in the 19th century. People just found out they should not produce a notch or an edge in locations where you have maximum stress. If you need a notch for some reason, then you should put it in a region where the stress is lowest. Okay, because a notch will always increase the stress at the tip of that notch. It also was found out that when you do a notch, you can look at the tip, and the tip can have a different radius. So if the tip of the notch is rounded, the notch is not as bad as when it's a sharp notch. So you could say in a rounded notch, the increase of stress is moderate. In a very sharp notch, the increase of stress is significant. And the ultimative sharp notch is when you have a crack. Yeah, imagine we would have a crack here. A crack is extremely sharp. The tip of a crack only has a roundness of or radius of, let's say, nanometers, and that means the stress concentration is very high. When we have here the material, and we pull here, and we look at the stress at the tip of that notch, of that crack, we can see that the stress is maximum here. We can have different loading. For instance, that is tensile loading. So we have this increase of stress. On the other hand, when we have a so-called shear loading, so above and below the crack or notch, it is shifted in different directions. We have two maxima under different angles. But what we can also see that the stress increase is very high. It can be more than 200% compared to the average stress here. So now we can say what is the functional behavior, and when we look at the stress components, we can say the stress increases with some factor divided by 2p r, and r is just the distance we have here. So that means the closer we get to the crack tip, the higher the stress is, and in a very brittle material it increases with square root of r, and that means we have a stress concentration or stress singularity. Okay. In that way, it is made clear that this increase of stress is, of course, an endangering factor. So when we regard stresses, we cannot just take an average stress, which we assume for our part, but we must take into account local stresses. And that's the secret of, let's say, of the success of mechanical engineering. People are addressing local stresses, and the better you can analyze local stresses, the better you can predict lifetime. In this case, this distribution was made with finite element method, but you can sometimes also do it with analytical method. So that's the so-called Snedden equations. You do not have to know these, but it is important to see that the local stress is depending on the average stress times the square root of the crack length. And the crack increases with the closeness to the to crack tip. So that means that formula also shows us that generally a part which has a larger crack or a deeper notch is endangered more than a part that only has a small notch or a small crack. So the radius is important. In a crack, the radius is almost zero, and then the crack length is the important part. Okay, a factor defining how severe crack is the crack intensity factor, and that's the stress. So it's a tensile stress multiplied with the square root of the crack length. And that means the crack intensity is a factor which defines a load in a material that has a crack. The factor of Q is something between 0.7 and 2.5. So there is a certain prefactor, but maybe just P divided by Q or so is maybe 1.5 or something like this. And when you take the square root of 1.5, it is something like 1.2. So that prefactor is not so important. Here I give you some examples from our research work. That is a crack on silicon. So if you dice silicon, you generate cracks, and when you regard such a crack, you can, when you know how deep it is, so the crack length, then you can compute what the stress is in your part. Okay, we are finished for today. I would like to thank you for your attention. Sometimes it would be helpful if you would give me a little more feedback, so I know you are still there and you are still alive. But let's try again in a week. Thanks for your attention.